Okay, so we're now recording. So if you'd like to type your name into the chat, now it will get recorded. And then I think Deborah will also be recording people's attendance today, but it's still good if you type your name into the chat so that I have a record as well. Okay, so a lot of people will come in. I hope you all had a good month. I know it's been a long time. So so welcome back, everyone. Some more people coming in. Okay. So let's actually, there is homework to go over, but maybe before we actually look at the homework, let's go and review a few of the facts that we learned last time, because it has been a very long time. Okay. So maybe even before we do anything specific, just remember that we were looking the last time at the graphs of these functions, y equals sine x and y equals cosine of x. And here, when we draw these graphs, we always think of x as being in radians. And so if you just remember what these graphs look like, y equals sine x was a wave that looked like this, where it went to 1, up to 1, and down to -1. And this was pi, and this was 2 pi, and this was 3 pi. And this here was minus pi, and minus 2 pi, and minus 3 pi. This is what the graph looked like for y equals sine x. And then y equals cosine x was basically the same graph, but it was shifted over a little bit. So it still went up to 1 and down to -1, but it looked more like this. Right? And so this here was pi over 2. This was 3 pi over 2. This point here was 2 pi. This was pi. And then over here we have minus pi over 2. And this is minus pi. And then minus 3 pi over 2. And this up here was going to be minus 2. Okay, it's not the specifics of the values will not be so important, but just want to remember that these functions, they look like waves. In particular, they're periodic. And what we see is anytime, so they're periodic with period 2 pi, which we saw. And remember, period 2 pi means that if I start with the graph, if I move 2 pi in the x direction, then the graph starts repeating itself, right? So I have a chunk that takes 2 pi, and then the next 2 pi is the same graph, and then the same after that, and it keeps repeating. And same thing with cosine of x. If I have cosine of x, if I go from 0 to 2 pi, that's the same thing as going from minus 2 pi to 0, and it's the same thing that'll keep going on forever. So the graph keeps repeating itself every 2 pi, right? In terms of algebra, the way that we think of that is we say that sine of x is equal to sine of x plus 2 pi, and cosine of x is equal to cosine of x plus 2 pi for any x, okay? And we had a few other observations that we made about these graphs. So we observed that cosine of x is an even function. That means that cosine of minus x is equal to cosine of x. And sine of x is an odd function, meaning that sine of minus x is equal to minus sine of x. And then we had two other facts. We had that sine of x plus pi, well, if you just add pi and not necessarily minus pi, then sine of x plus pi is going to be minus sine of x instead of sine of x. And cosine of x plus pi, if you only add pi, then, well, you don't get cosine of x, but you get minus cosine of x. Okay, so these were things that we observed from looking at the graphs. Okay, and so by the way, for those who just came in, it's good to see everybody again because it's been so long. So you can please type your name into the chat if you haven't done so already, so that way we have your record for attendance. And thank you again for everybody who reached out to me about my uncle over WhatsApp. Okay. So good. So these are our observations about sine and cosine, and we're going to need these observations in order to do the homework problems, which we'll spend, I think, maybe a lot of time going over because we're doing kind of only one other main derivation today. Okay, so before we go and look at the homework problems, does anybody have any questions over any of these facts here on this page that we observed in earlier lessons? Okay. Okay, so let's now go back and look at the homework, which was assigned 4 weeks ago, so maybe people don't remember it. So number one is knowing only what we know about cosine. Can we determine whether cotangent of x, secant of x, and cosecant of x are even or odd functions? And we want to do this without drawing the graphs, right? Using only algebra, right? So we want to do this using only algebra. So let me just recall, I'll write it down on this page so we don't have to keep writing it down. So remember that sine of minus x is equal to minus sine of x. That means it's an odd function. And cosine of minus x is equal to cosine of x. That means that it's an even function. Okay, so this is just going to be something that we're going to use. So let's look at this. Let's do each one. So we have cotangent here, we'll have secant over here, and we'll have cosecant here. Well, cotangent of x, let's remember, is cosine of x over sine of x. Secant of x is 1 over cosine of x. And cosecant of x is 1 over sine of x. Okay, so let's look at the first one. If we wanted to figure out whether cotangent of x is an odd function or an even function, or maybe neither, what do we have to do with this expression? So if cotangent of x is cosine of x over sine of x, what would we do with this expression to check whether this is an odd or an even function?
But
Yeah, Gabriel?
yeah, if we divide a negative by positive, we get negative values.
Right,
If we replace some value with negative.
Right, so it's going to be negative, exactly. Let's do it just a little bit more, in a little more detail, right? So what happens is if we have cotangent of minus x, this is cosine of minus x divided by sine of minus x. And now we have our chart. We remember what's going on with sine and cosine, right? So cosine of minus x is the same as cosine of x. Sine of minus x is the same as minus sine of x. And this is minus cosine of x over sine of x. And this is exactly minus cotangent of x. Right, so as Gabriel said, when we plug in minus x, we're going to get, positive divided by a negative is going to be a negative. And so we end up with minus cotangent of x. And that means that cotangent of x, if you plug in minus x, you get minus of the function. That means this is an odd function. Okay. Right. And so this gives you an odd function. So secant and cosecant work exactly the same way, but it's a little bit easier, right? So for secant, you just have that secant of minus x is 1 over cosine of minus x. And well, this is 1 over cosine of x, and that's equal to secant of x. So here we have that secant of minus x is the same thing as secant of x. That means that secant of x is an even function. And then lastly over here with cosecant, we can do the same thing, right? So cosecant of minus x is 1 over sine of minus x. From our facts over here, we know that sine of minus x is minus sine of x. So this is 1 over minus sine of x. And that's the same thing as minus cosecant of x. Right, and so cosecant of minus x is minus cosecant of x. And that's, again, the definition of an odd function. So this is what we get for these three things. So cotangent is odd, secant is even, and cosecant is odd. And so in general, I don't memorize that, right? If you woke me up in the middle of the night and said, is cosecant an even or an odd function? Like, I wouldn't just be able to tell you. I'd have to think about it. If you woke me up and asked me about sine or cosine, I'd be able to tell you. Those are the only two things that I have in my long-term memory. Everything else, I just derive from what I know about sine and cosine, okay? And so that's what we see going on here, right? Everything is getting derived from what we know about sines and cosine. Cotangent is cosine over sine, secant is 1 over cosine, and cosecant is 1 over sine, and we can use that in all of these cases to determine whether the function is an even or an odd function. Okay. All right. So, any questions about this problem?
Yes, Robert.
Yes, Abraham.
Looking at the first problem there, we have full son of x or minus son of x. But
Yeah.
now coming back next, we have minus full son of x or son of x. Why the negative sign to the son excepting the full son?
Ah, right. So we're using these facts, right? So what we saw before, and granted it was a month ago, is that sine of minus x is minus sine of x. But cosine of minus x is just cosine of x, right? These are the identities that we have. This is what we have to know that sine of x is an odd function and cosine of x is an even function. This comes from looking at their graphs. So now over here, we're going to plug in minus x for x. So we're going to get a minus x and a minus x. But with cosine, the minus just disappears, and we just have cosine of x. Whereas for sine, the minus x doesn't disappear, but the minus actually gets pulled out, and so we get a minus sign over here. So because cosine is even, cosine minus x is just cosine x. But because sine is odd, sine of minus x is minus sine of x. So we end up with only one minus sign here, and then since we have one minus sign in the fraction, we can move it outside the fraction. And so that's what we end up with. Does that help?
Thank you.
Good. Okay, you're welcome. Other questions? Okay. So let's look at exercise 2. So we want to find the smallest positive number alpha such that cosine of 2x is equal to cosine of 2 times x plus alpha for all x. And whatever number this is going to be called the period of the function cosine of 2x. Okay? So we want to know what is an alpha that if we, so by the way, yeah, this really should be in parentheses over here. So that cosine of 2x is the same thing as cosine of 2x plus alpha. So does anybody have an answer for like, and so let me again say, what do we recall? We recall that in general, if I just have regular cosine of x is equal to cosine of x plus 2 pi. And furthermore, 2 pi is the smallest positive number with this property. Okay. 2 pi is the smallest positive number with this property. And so, and sometimes this is called the period, right? So 2 pi is the period of cosine x. So what this question is asking you is, what is the period of the function cosine of 2x? So what's the smallest positive number alpha that you can think of that you can plug in here that makes this identity correct? So does anybody just have a number alpha that you can plug in here to make the identity correct, even if it's maybe not the smallest one? I mean, of course, alpha equals 0 works. That just says cosine 2x equals cosine 2x. But can you find some alpha that's positive that works? Okay, well, let's think about this, right? We know that cosine of anything is the same as cosine of that thing plus 2 pi, right? So if I have cosine of 2x, so maybe I won't write this down just yet. So let's observe that cosine of 2x is the same thing as cosine of 2x plus 2 pi, right? Because this, you can always add 2 pi to anything, and that always works. So in that case, what we have is that cosine of 2x is the same thing as cosine of 2 times, what we can do here is x plus pi. Okay, because this is 2 times x plus pi is the same thing as cosine of 2x plus 2 pi. Okay? So what this means is if we add pi to x, then this does not change the function. This does not change the function cosine of 2x. Okay, so the correct answer for this problem is pi, right? Because if I take alpha equals pi, then 2 times x plus alpha is going to be 2x plus 2 pi. And that means I'm only adding 2 pi to the argument of cosine, to the 2x. And that's not going to change the function. And so visually, what this means is that the graph of cosine 2x repeats itself every pi units horizontally. Okay. And so let's see this graphically. Let me show you on Desmos, which we've used before, this graphing calculator. So let me share my screen, and I'll show you what happens here. So let me share my screen to do Desmos. Here we are. Okay, so I'm going to share my screen. So if I have y equals cosine of x, then I get this graph over here. And one thing that you can see is that this graph repeats itself every 2 pi, right? It goes down and then up. It does one wave every 2 pi. But if I now replace cosine of x with cosine of 2x instead, what's going to happen is the graph is going to repeat itself every pi instead of every 2 pi. And what that means is the wave is going to get compressed in the horizontal direction by a factor of 2, right? So cosine of 2x, what's going to happen? Now you see, like, instead of cosine of x, I get this wide wave, but cosine of 2x is now a compressed wave. And what you see happens here is that you get a full wave every pi units in the horizontal direction instead of every 2 pi units. And in fact, if I multiply x by bigger numbers, it's going to get compressed even more. So if I do cosine of 4x, then the wave is going to get compressed by another factor of 2. So we'll see that 4x, the wave goes much faster, and 8x starts to get really fast, 16x. And then sometime if I start taking really big numbers, then you won't even be able to see it. If I do 160x, boom, it's just what it looks like. The line is too thick. You can't even see it, right? I mean, even 30x is already barely. How many x's do we have to do before it becomes invisible? 35, 50 is basically done for, and 60 is just going to be like nothing, 70, So, but again, remember, cosine of x versus cosine 2x, that 2 compresses the x by 2, okay? And so we saw that for cosine of 2x, when you plug in x plus pi instead of x, you get the same answer. Whereas for cosine of x, you have to plug in x plus 2 pi instead of x to get the same answer. Okay, any questions about this example? Let me stop my share. Let me share my screen again. Here we are. Okay, great. Okay, so the answer to this question is pi. Okay, so pi is the smallest positive number you can do because pi in this function gives you 2 pi in the other function. Everybody okay? Okay, so let's look at homework exercise 3. So the same as question 2, but now we're using the function cosine squared of x instead of cosine 2x. So the question is asking, what is the smallest positive, and this should not say integer, this should say number, smallest positive number alpha, such that cosine squared x equals cosine squared of x plus a for all x. And for this, we want to just recall that cosine of x plus pi is equal to minus cosine of x. Okay? So what does that tell us about cosine squared of x plus pi? So if I square both sides, that's the same thing as minus cosine squared of x, right? No, not minus cosine squared of x. That's the same thing as minus cosine of x squared, which is the same thing as cosine squared of x, right? Okay. So that's cosine minus cosine of x squared, which is the same as cosine squared of x. Okay. So, so this is what we have. And so in particular, what we see is that this cosine squared of x plus pi is equal to cosine squared of x. Okay, and so that again tells us that alpha equals pi works. And so I'm not going to prove it, but it turns out that this is the smallest positive number that works. Okay. And maybe again, we should look. If we have cosine of x, we know that the wave repeats itself every 2 pi. Let's see what happens when we graph cosine squared of x, right? So what should happen is that now, again, we'll get a period of pi. We'll get something that repeats itself every time you move pi in the horizontal direction. So let me show you Desmos one more time. So here we have y equals cosine of x, right? Y equals cosine of x. Now what happens if we do cosine squared of x? Where are we here? So if we do cosine of x, and now I do squared, now what do we get? It looks kind of like a cosine wave, right? But it's now completely above the x-axis. That makes sense because it's a square, right? So this function should never be negative. And what happens, we see that the waves also get smaller, right? The waves become every pi. So they actually get reduced in the vertical direction, but they also get smushed in the horizontal direction, right? You get a full wave between pi and minus pi and 0, and then between 0 and pi, as opposed to without this, where you get a full wave, let me just say with a 1 here instead, right? With a 1, you get a full wave every 2 pi, and with a 2, you get a full wave every pi. And it turns out that I think this pattern doesn't necessarily hold anymore. Like if you do cosine x to the 4th, you're not going to get any bigger waves. You're just going to get waves that look a little deeper. Cosine x to the 4th looks like this. Cosine x to the 6th looks like this. Cosine x to the 10th, you're getting these weird functions that kind of spike up. If you do 100, then it's an even bigger spike, and 1,000. So I mean, Desmos is nice because you can just kind of like play around with these functions, see what happens when you change things. But for this function, really, we have cosine x to the 1, which is your standard cosine graph, and then cosine x squared, which is going to give you waves that cycle at twice the speed. Okay. And if you did an odd power, something like cosine x cubed, then it's going to look a lot like the original cosine graph, but it's going to have this weird it's going to have these kind of x cubed looking graphs in the middle. So it's going to be much more wobbly. Cosine x to the 5th, to the 7th, to the 9th. These odd ones all look the same. If I start doing very high odd powers, they end up having these positive and negative spikes. So this is nice to play around with and see if you can try to figure out like how you explain like where these spikes come from. What about 299? What about 2999? These bigger spikes. Why does this happen? So this is, so for this problem, all that we care about is cosine x squared, but it's nice to have Desmos to be able to play around with to see, how this stuff works. Okay. All right, so I'll reshare my regular screen again. Give me a second. Zoom, share screen. Okay, great. So any questions about this example? Okay, so let's move on to the main topics for today. Yeah, I don't think we need to talk about that. So the main topics for today, which are what are called the addition and the subtraction formulas in trigonometry. Okay, so for instance, so we have some identities already. We have some basic identities like cosine of x equals cosine of minus x, things like this. But what if I have two angles and I want to find cosine of their difference? So what we're going to spend most of today doing is deriving this formula for cosine of a minus b. How do we do that? Well, the first thing that you should know, and this is a mistake that a lot of people make, that a lot of your students will make, is that, and a lot of American students make this mistake also. When I teach this stuff, students are making this mistake all the time. So cosine of a minus b is not the same as cosine of a minus cosine of b. You can't just distribute the minus out, okay? And so why is this not true? Well, first of all, there's just kind of no reason that it should be true, right? There's no distributive law for trig functions or anything like that. But maybe, what do I want to say? But let's do an actual example that shows that this can't possibly be true. So let's let A be equal to 60 degrees and B be equal to 30 degrees. Then we have that cosine of A minus B is equal to cosine of 60 degrees minus cosine of 30 degrees. And if you remember your tables, cosine of 60 degrees is equal to 1/2, and cosine of 30 degrees is square root of 3 over 2. So this is 1 minus square root of 3 divided by 2, right? But, oh, sorry, I did the wrong side. Sorry, let me erase this. That's going to be the other side. Sorry, cosine of A minus B is cosine of 60 degrees minus 30 degrees, which is equal to cosine of 30 degrees, which is square root of 3 over 2. But if I take cosine of A minus cosine of B, if I take cosine of A minus cosine of B, this is equal to cosine of 60 degrees minus cosine of 30 degrees. And this is the calculation we already did. That's 1/2 minus square root of 3 over 2. And that's equal to 1 minus square root of 3 over 2, right? And these two things are not equal to each other. Right? So this means there's no possible way that we could have the identity cosine of A minus B equals cosine A minus cosine B, right? This is not possible. We don't have an identity like this, right? Because if it was an identity, it would have to work for every choice of A and B, right? And this identity does not work, okay? Even for this choice of A and B, 60 and 30, it doesn't work. And in fact, if you try to plug in almost anything at all, it's not going to work. Okay, so this is almost never, ever going to work. Okay, so whatever the correct formula is for cosine of A minus B, and maybe you know it, maybe you've memorized it, but certainly cosine A minus cosine B is not it. It is not going to be the right formula. Okay, does anybody have any questions on why this can't possibly be correct based on this example? Okay, so give me 1 second. Okay, so what is the formula? Let's try to actually derive it. So the formula that we're going to derive is going to be based on this picture over here. So let's say that we want to figure out what is cosine of a minus b. Well, let's try to draw a picture where this appears. So let's say that we have two angles B and A. So the labeling here on this diagram is a little misleading. So let me try to make the labeling a little clearer. So if this is A minus B, this angle here is going to be B, and then this bigger angle here is going to be A. Right, so I'm just drawing the angles there, A and B. I think the labeling on the diagram is a little misleading, and then A minus B is correct here. And so the idea is, what happens? If I draw this ray over here at an angle of A minus B, then by definition, where does it hit the unit circle? Well, the x-coordinate is cosine of A minus B, and the y-coordinate is sine of A minus B. So now let's imagine I take this triangle and I rotate it counterclockwise an angle of B. So what happens? If I take this triangle and I rotate it counterclockwise, well, I have that so if I take this triangle and I rotate it counterclockwise, then this goes from the angle 0 all the way up to the angle B, and this point goes from the angle A minus B. Well, I have to add B to it, so that goes to the angle A, which is A minus B plus A. So this triangle over here is just the rotation of this triangle over here, right? It's just the rotation of this triangle over here. Okay? This triangle here is the rotation of this triangle here. Okay? Okay. So what does this tell us? Give me 1 second. I just want to check something, and then I will come back and we'll do this. 1 second. Oh, okay, great. Okay. Good. Okay. Okay, so what do we have to do? Well, if this one triangle is just this triangle rotated, then what's our takeaway here is that both triangles are congruent. And so that means, in particular, if I label these purple sides have the same length. So this purple line here has the same length as this purple line here. So the purple sides have the same length. Okay, so the purple sides have the same length as each other. And we're going to use this identity with the purple sides in order to prove this identity. Because what we're going to see is that the length of this side is going to involve cosine of A minus B, and the length of the other sides is going to involve some cosines and some sines. But actually, since we know that these two sides have to have the same length, we'll be able to get an identity of one in terms of the other. Okay? All right. Any questions there? Okay. Okay, great. So let's actually do the derivation. So how are we going to do this derivation? So the idea is, so one line segment goes from, what does it go from? It goes from, well, what was the points? It goes from cosine A sine A to cosine B sine B. So from cosine A sine A to cosine B sine B. The other one goes from, well, what do we have? It goes from cosine A minus B sine A minus B down to this point. But this is the unit circle, right? So this is just the point 1 comma 0, right? So this goes from cosine of A minus B sine of A minus B to 1, 0. Okay. So now we're just going to compare the distances and set them equal to each other. So we're going to set the distances equal to each other. All right, so what happens when we set the distances equal to each other? So, well, what's the distance from cos A sine A to cos B sine B? Well, by distance formula, we get that that is the square root of cosine of A minus cosine of B squared plus sine of A minus sine of B squared. That this should be equal to the square root of, what's this distance? It's cosine of A minus B minus 1 squared. So cosine A minus B minus 1 squared, and then plus, we have sine of A minus B minus 0 squared. Okay, right? So these are the two things that we're going to set equal to each other. Okay. All right, any questions so far? Okay, and now the rest is algebra, and we're just going to get the identity. So first thing, of course, we can square both sides because we have square roots, so we can just get rid of the square roots. So cos A minus cosine B squared plus sine A minus sine B squared equals cosine of A minus B minus 1 squared plus, and here we can just say sine of A minus B squared, right? So now let me just expand out all of the squares. So this is cosine squared A plus cosine squared B minus 2 cosine A cosine B plus sine squared A plus sine squared B minus 2 sine A sine B. That this is equal to, now I have to do this square. So that's cosine squared A minus B plus 1 minus 2 cosine A minus B. And then last thing here is we have plus sine squared of A minus B. Okay, so I did maybe the algebra a little fast, but all I did was square this out. So this became this. I squared this, which became this. I squared this, which became this. And then I squared this, which is just one term over here. And now I am a little worried that I did something dumb here. So let me, oh, no, we're good, we're good. Okay, great. So, let me start doing some canceling. Okay, so what happens here? Well, I have a lot of terms that I can simplify here, right? So here I have cosine squared A plus sine squared A. That's equal to 1. And I have cosine squared B plus sine squared B. That's equal to 1. And I have cosine squared AB plus sine squared AB. That's also equal to 1. Remember that we have this identity that no matter what, we have cosine squared x plus sine squared x is always equal to 1. So applying this identity, what do we get? I get 1 plus 1 minus 2 cosine A cosine B minus 2 sine A sine B equals, and again, here I have 1 plus 1, 1 plus 1, and then minus 2 cosine A minus B. Okay, so now the 1's cancel out. So I have a 1 and a 1 here and a 1 and a 1 here. So I have minus 2 cosine A cosine B minus sine A sine B equals minus 2 cosine of A minus B. But I've got these minus 2's everywhere. So let me divide out by minus 2 on both sides, right? So I'm going to divide out by minus 2. Then I get cosine A cosine B plus sine A sine B is equal to cosine of A minus B. Okay, and this is the formula that we want. Okay. All right. So this is what happens when we derive everything. Okay. So we start, remember, so this is the whole derivation. We're done. So we have our formula. Oh, oopsie. Cosine of A minus B is equal to cosine A cosine B plus sine A sine B. Not what you'd maybe guess if you just had it, but this is what comes from the formula by comparing the lengths of these two line segments and showing, and you know that they're equal to each other since one is just a rotation of the other one. And since they're equal to each other, you can write down their lengths using the Pythagorean theorem. That's how these lengths go. And if we write down the lengths with the Pythagorean theorem, they're equal. And so if we just look at the equation that you get from setting them equal and simplify the equation, then you end up getting exactly this formula for cosine of A minus B. All right, so we'll do an example of this. But before that example, are there any questions about the derivation of this, how it works?
Yeah.
Yeah.
Yes, sir. No,
Yes.
sir.
Good. Yeah, Prince.
French.
Mm-hmm.
Thank you. I was not in a class, for at least go have you in a class now. But I want to know. So all of those things came from the cosine square x plus sine square x equal to 1. So it's where this formula derived from actually.
So I'll show you. So this is one that we did a little while ago, but so remember, so if you're on the unit circle, so if this is a unit circle that has radius 1, if I take any point over here, if this is some angle x or theta, maybe we'll call it theta, this is going to be cosine of theta sine squared of sine of theta. That's what the point is, at an angle theta for the unit circle. And so since the circle has radius 1, so that means that the distance from the origin to this point is 1. And that exactly tells us, so what is maybe we can even do it with a right triangle with Pythagoras' theorem. So this side has length, sine, well, the length of this is actually going to be minus sine of theta, but that's fine just because it goes downward. So sine of theta is negative, and this here is going to be cosine theta, and this is 1. So by Pythagoras, what do we get? We get, minus sine of theta squared plus cosine of theta squared is equal to 1 squared. And this just simplifies to sine squared theta plus cosine squared theta equals 1. Right? And it doesn't matter what my theta was. I just picked some random angle. It could be any angle I want, and you'll always be able to draw this right triangle in this unit circle, which means that the radius is 1, and that radius is going to be a hypotenuse of a right triangle, and the other sides of the right triangle are going to be sine and cosine of the angle, or plus or minus sine and cosine. So when you square it out using the Pythagorean theorem, you get sine squared plus cosine squared equals 1. So this is, one of the most important identities in trigonometry, and it's used all over the place to derive other things.
Okay.
Does that help?
So getting it. So it doesn't matter where the one is placed. Like for instance, if we are taking one and then we get to where the negative sign theta is located, will it be
Right.
the
It
same
doesn't
thing?
matter because you're going to square it.
Okay.
So the negatives go
Okay.
away. Yeah.
Okay.
Yeah. The negatives go away because you're squaring.
Thank you.
Okay. You're welcome. So other questions? Okay, so let's check this at least. This is a formula. It's some complicated algebra. Maybe I made a mistake. We should at least check, right? So let's check for the same example. So let's check. Remember, so our formula is that cosine of A minus B is equal to cosine A cosine B plus sine A sine B. That's the formula that we got on the last page. So let's check, for an example, let's do the same example. Let's say that A is 60 degrees and B is 30 degrees. So then the left-hand side, LHS, that's left-hand side, we have cosine of 60 degrees minus 30 degrees. That's equal to cosine of 30 degrees. And that, if you recall, is square root of 3 over 2. Now, what about the right-hand side? What happens on the right-hand side? Well, we get cosine of 60 degrees times cosine of 30 degrees plus sine of 60 degrees times sine of 30 degrees. Right? I'm just plugging in A equals 60 degrees and B equals 30 degrees. So let's write this. So cosine of 60 degrees is going to be 1/2. Cosine of 30 degrees is square root of 3 over 2. Plus sine of 60 degrees is square root of 3 over 2. And sine of 30 degrees is 1/2. Right? So if I do this all out, what do I get? I get square root of 3 over 4 plus square root of 3 over 4, right? This is multiplication here. And when I add them together, I get 2 square root of 3 over 4, and this is the same thing as square root of 3 over 2. So at least in this example, this should give us some confidence. It's verifying that the formula is actually correct. Right? We plug in an example with 60 and 30, and we get something correct. And you can plug in other things. Yes, Princeton? Sorry, Prince. Prince, yeah.
So you use the angle of 30 and 60 degree.
Yeah.
So if we use the angle of 60 and 90 degree.
Yeah, that'll work also. Should we do it? Let's do it.
Yeah, we get no problem. As to whether it will go checking.
Yeah, let's do another one. Let's say that A is 90 degrees and B is 60 degrees. Okay, so then the left-hand side, again, is going to be cosine of 90 degrees minus 60 degrees, which is cosine of 30 degrees, which is, again, square root of 3 over 2. And then on the right-hand side, we have cosine 90 degrees, cosine 60 degrees, plus, so this is the right-hand side, plus sine of 90 degrees, sine of 60 degrees. Let's see what we get. Cosine of 90 degrees is 0 times cosine of 60 degrees is 1/2. Sine of 90 degrees is 1 times sine of 60 degrees is square root of 3 over 2. And so you get 0 plus square root of 3 over 2, which is equal to square root of 3 over 2. And it also works. So no, the formula is amazing. I mean, it always works, right? And it has to work because we proved it, right? We did what we did on the last page was a proof. It works for every possible A and B. So it's good to check by plugging in some values that we know. But this also works when A is 47 degrees and B is 15.28157 degrees, right? I mean, you're not going to be able to calculate that, but the formula is still true, right? It has to work for every possible angle. Okay? So this is our nice formula for cosine of A minus B. And it's not the simplest formula, but it's the one that's actually correct. Whereas something that looks simpler, like cosine of A minus cosine of B, is actually incorrect. We showed by a counterexample that that cannot be correct. Okay?
Okay.
All right.
Thank you, sir.
Okay. You're welcome. Any other questions? Okay. Great. So, you know, I encourage you try it on your own with whatever angles you want. Try 90 and 45 or whatever. We're not going to do it now, but try it on your own and it will also work. Okay. So, okay, good. So we have this formula. So now our question is, how can we use this to get a formula for cosine of a plus b, right? I started with cosine of a minus b because it makes the geometry easier. But what if we wanted to get a formula for cosine of a plus b, right? That's a basic formula that we'd like to have. Well, what do you do? Well, I can do this. I can say cosine of a plus b. Well, a plus b is the same thing as a minus minus b, right? That's the same thing as a plus b. And now we can apply the subtraction formula. Right, now we can apply the subtraction formula, right? Because we know what we have when we have a minus b. So now I want a minus minus b. So we just plug in this minus b for b in the subtraction formula. So we apply the subtraction formula with minus b in place of b. Right? So this means that cosine of a plus b is equal to cosine of a minus minus b, which by the formula is cosine of a times cosine of minus b plus sine of a times sine of minus b, right? I'm doing the exact formula, but anytime I see a b, I'm plugging in a minus b instead. Okay? And so now we've got to do our even and odd function stuff, right? So cosine of minus b, remember, is just the same thing as cosine b, right? So this is just cosine of a times cosine of b. And sine of minus b, remember, was an odd function, so that's going to be negative sine of b. So this is plus sine of a times negative sine of b. Or in other words, cosine a cosine b, the minus can go out, right? So it's going to be minus, minus sine a sine b. Okay? And so this is our formula. So the formula is that cosine of a plus b is equal to cosine a cosine b minus sine a sine b.
You hear that over?
Yes, Clinton.
Yeah, thank you for this division. It's actually cool. But I want to know if we can derive cos of a plus b from that triangle, from that unit circle as well.
It's not that easy to do. You can do it, but it's going to be more complicated because if you have cosine of a plus b, it's not easy to like rotate that. And I mean, okay, you can. You can. I'll show you how. Maybe let me just briefly sketch it. So the idea is, you know, this diagram has too much writing on it already. Let me just do another page to see how you would do it. So here's what you do. If you wanted to derive it, let's say that I had an angle here in the unit circle, and I had an angle here that this angle was a plus b. So that this point over here would be cosine of a plus b, sine of a plus b. Then I can draw the same unit circle where I rotate it so that I've got an angle of b up here and an angle of a down here. And so this is cos b sine b. And since the a here is actually counted under the x-axis, this over here is actually going to be cosine of minus a and sine of minus a. Okay. And so again, this point here is 1, 0, and you can do a similar proof where you set, let me make them purple again, because that's what we use. So the length of this purple line segment here is equal to the length of this purple line segment, because both of these are an angle of a plus b. And so if you rotate this diagram over here, you get this diagram. So by calculating the length of this line segment and setting it equal to the length of this line segment, then you'd be able to get a formula for cosine of a plus b directly.
Oh, okay. All right.
Okay.
So
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 that's
we rotate we rotate the angle there a units in the negative axis.
exactly right. Yeah. So this over here is supposed to be the horizontal x-axis here, right? Yeah. I'll draw the axes, right? It's supposed to be the axes. Yeah, exactly. So
Okay,
you
yeah,
rotate it so that you
yeah.
got B above the axis and A below the axis, and that's how you can get formulas that you know for the points.
So for the first figure,
Yep.
a plus b, a plus b. Is it? Oh, okay. We rotate that. Okay. All right. I thought it was a simple position.
Sorry. I think you muted yourself. Okay. All right. So maybe let me not say more about this. We can talk about it later. Okay, but yeah, so you can derive this directly from the unit circle if you want to, or you can derive it from the fact that you already know the subtraction formula, and you can get the you can get this. So it's the same as the subtraction formula. Just to memorize it, it's just the plus becomes a minus. So with these cosine formulas, you want to think that whatever sign you have here, so whether it's a minus or a plus, in the actual formula, the sign changes. So the minus changes to a plus, and the plus changes to a minus. Okay. Okay. So let's do maybe one more formula today. Okay. So we want formulas for sine also, right? So how do we get a formula for sine? Well, we can do something, we could do a unit circle derivation also. You'd have to use the 0.01 instead of the 0.10, but let's just derive everything from this cosine formula. So it would be nice to have a formula for sine of a plus b and sine of a minus b, right? So first, let's just prove that sine of x equals cosine of pi over 2 minus x, right? So this is going to be easy because we can just use the subtraction formula. Right? So cosine of pi over 2 minus x, if you recall the formula, this is cosine of pi over 2 times cosine of x plus sine of pi over 2 times sine of x, right? This is the formula. But cosine of pi over 2, right, is just 0, and sine of pi over 2 is just 1. So this is just equal to 0 cosine of x plus 1 sine of x, and this is just sine of x. Right? So this is a very easy proof of the identity that we already knew for acute angles using right triangles, right? I mean, if x is like 30 degrees, remember pi over 2 is 90 degrees. So if x is 30 degrees, this angle would be 60 degrees. And we know that sine of 30 degrees is cosine of 60 degrees because they're the opposite angles in a right triangle. But with this proof, we see that the formula works no matter what. It doesn't matter whether you have acute angles or, your x could be 150 degrees, or it could be a negative angle or whatever. It can be any real number, that this formula will always work because it comes from the subtraction formula for cosine. Okay. So this is a quick, it'd be called a lemma sometimes in mathematics. It means a small theorem that you prove before you want to prove a big theorem. So this is telling us that cosine of pi squared minus x is equal to sine of x. So we're going to use this to get these formulas for sine of a plus b and sine of a minus b. And in fact, I'm only going to prove one of them, and I'll leave the other one as an exercise. So before we go on to the real proof, which will be the last thing we do today, does anybody have any questions about how we got that sine of x is equal to cosine of pi over 2 minus x? It's just a direct application of the subtraction formula. Right, and maybe I should just recall over here, if you haven't dealt with your radians in a while, recall that pi over 2 radians equals 90 degrees. Okay, so now that we know this, let's try to do. So we want to do sine of a plus b. From what we've shown before, sine of a plus b is cosine of pi over 2 minus a plus b, right? Because for any angle, we have that sine of x is cosine of pi over 2 minus x. So we can write sine of a plus b equals cosine of pi over 2 minus a plus b. And now all I'm doing is regrouping the parentheses here. So I get, that's the same thing as this is, right, cosine of pi over 2 minus a plus b. It's minus the a and minus the b. So I can write this as cosine of pi over 2 minus a minus b. So now I'm just going to use the cosine subtraction formula again, right? So we have that sine of a plus b is equal to cosine of pi over 2 minus a minus b. And by our subtraction formula, what is that? Well, it's just cosine of pi over 2 minus a times cosine of b plus sine of pi over 2 minus a sine of b. Okay? And well, what is this? Well, cosine of pi over 2 minus a, we proved on the previous page, this is sine of a. And then sine of a times cosine of b. That stays there, right? Remember, this cosine of pi over 2 minus a is the same thing as sine of a. And then what do we have over here? So plus, well, here we have sine of b. That's going to stay. And then sine of pi over 2 minus a. Well, this is the same thing as cosine of pi over 2 minus pi over 2 minus a. Right? Again, using this same formula. Right? Sine of any angle is the same as cosine of pi over 2 minus that angle. Right? The same formula that we have. But now, simplifying this all, this is sine a cosine b plus, well, what's pi over 2 minus pi over 2 minus a? That actually is just equal to a. So this is just plus cosine of a sine of b. Okay, so the formula is that sine of a plus b equals, so for the sine formulas, you have to mix and match the cosines and the sines. So sine of a plus b equals sine of a cosine of b plus cosine of a sine of b. Okay. And so again, we get it from the cosine formula, but we have to be a little bit tricky here. We have to substitute, we have to turn a sine into a cosine by using this identity, that cosine of pi over 2 minus x is the same as sine of x. And we actually use that identity in a few places in the proof. We use it to get this first equality. We then apply the subtraction formula, and then we have to use it again to turn this cosine back into a sine, and we have to use it again to turn this cosine back into to turn this sine into a cosine. But in the end, we get this very clean formula, sine a cosine b plus cosine a sine b. And maybe as one last thing, let's just check again. Let me take a equals 30 degrees and b equals 60 degrees. So sine of a plus b is equal to sine of 30 degrees plus 60 degrees, which is equal to sine of 90 degrees, which is equal to 1. And on the other side, we have sine a cosine b plus cosine a sine b. Well, this is equal to sine of 30 degrees cosine of 60 degrees plus cosine of 30 degrees sine of 60 degrees, right? And what is this? Well, sine of 30 degrees is 1/2. Cosine of 60 degrees is also 1/2. Plus cosine of 30 degrees is square root of 3 over 2. Sine of 60 degrees is square root of 3 over 2. So this comes out to be 1/4 plus root 3 over 2 times root 3 over 2 is 3 over 4. And that turns out to be 1. Right? So we get, again, that this identity works when we plug in 30 and 60. So this is not a proof, it's just one example, but it at least confirms our intuition, right? It confirms our proof that we didn't make a mistake, right? I plug in some angles here and we get something that actually works. Okay. So this is the formula for sine of a plus b. Okay, it's sine A cosine B plus cosine A sine B. So next time we'll recall all of these formulas. But, and this is the last thing we're going to do. I'm going to show you the homework afterwards. So before that, any questions on this?
It's actually clear for me.
Okay, great. Okay, so what are the homework problems? So the first one is evaluate cosine of 15 degrees and sine of 15 degrees using our subtraction formula for today. And the hint is how can you write 15, maybe let's say just cosine of 15 degrees. Okay, just cosine of 15 degrees using our subtraction formula from today. And so the hint is how can you write 15 degrees as a minus b when a and b are angles whose sines and cosines you know. So you can do that to figure out what cosine of 15 degrees is, even though cosine of 15 degrees is not one of the standard angles that you measure, that you memorize. So question 2 is derive formulas for cosine of 2a and sine of 2a from the addition formulas we've proven. Cosine of 2a is not going to be 2 cosine a. You can verify that doesn't work. Sine of 2a is not going to be 2 sine a. You can verify that doesn't work. And then homework number 3 is, can you derive a formula for tangent of a plus b in terms of tangent a and tangent b? And the hint here is use the formulas for sine of a plus b and cosine of a plus b and simplify. Okay. So, all right. So these are 3 problems that should be solvable given that you know these formulas that we talked about today. And so I'll say, again, thank you for your attention. This is not going to be April 5th. Unfortunately, this is actually going to be April 19th. We're not going to be able to meet next week because I have a meeting that I have to go to. And I wanted to check. I think actually is that a oh, it's a holiday in Liberia anyway, April 12th, Fast and Prayer Day, right? So in any case, we won't meet on Fast and Prayer Day, and our next meeting will be on April 19th. Okay, so we'll discuss further trigonometric identities following from the addition and subtraction formulas. So we're going to talk about double angle formulas and half angle formulas.
Yeah. Thank you for the class today, Dr. Robert.
All right, you are welcome. Okay, let me stop the recording. Oh, actually, before I stop the recording, anybody who hasn't put their name in yet to the chat, please do so that we have a record of your attendance. Okay. And as always, thank you so much for coming. I'm sorry that we had so long between classes and that we have another break next week, but we will, yeah, not have class on Fast and Prayer Day, and then we'll have class again on April 19th. Okay. So I will stop the recording now.